But we'll now move to a much more pedagogical format and teach you on the blackboard, very old-fashioned, about out-of-equilibrium processes, Langevin equations, this sort of thing. So I'll leave it to you, Letícia.
Thank you, Jaron. Thank you. Yeah, so I think that schools should be on the blackboard. So I do that. So this is my name, very long. And my email, it was on the slide, first slide of my talk on Wednesday. So if you need it, I can give it to you again. In the first slide, there was also a little logo, which I didn't comment upon, which was about this. So this is a journal. It's based in Trieste, ICTP-SAIFR in Trieste. And it's a journal which is devoted to statistical physics. It's a very nice journal. So, I suggest you to have a look at the papers over there if you haven't, and consider it for publication in the future. And in particular, there is Fernando Mes, whom you may know from Porto Alegre, and Ezequiel Ferrero from Bariloche, who's coming next week, who are co-editors of this journal. And I'll surely recruit some other ones, because I'm the editor-in-chief, actually. So I'll recruit some other ones from South America soon. So the idea is to expand and not, be just a European journal, in a sense. So is this big enough for those who are far away? Yeah, OK. So I'm going to talk about non-equilibrium, say macroscopic, complex systems. And of course, there are many adjectives here. So let me discuss a little bit each of them. Non-equilibrium, well, actually, all the speakers, I think, are telling you things about non-equilibrium systems. It's, of course, main topic at present. There are many applications. I'm going to discuss a little bit consequences of what we'll present on glassy dynamics. And I think that Mathieu Villard may have already told you something about this. A little bit of active matter, we heard a lot. So these are slightly different situations. These are systems which are in relaxation. We don't force them. We just let them evolve after preparation under certain conditions. And it turns out that their evolution occurs out of equilibrium just because they don't have enough time to reach equilibrium during the experiments or the numerical simulations that you can make. So if you want to describe their behavior and say things about possible applications, if you're interested in industrial applications and things like that, necessarily you have to deal with an out of equilibrium situation. And I will be more precise about, what does it mean to define or estimate an equilibration time for a system, and when can it be so long that you don't reach it in experimentally relevant times, in particular because it depends on system size, say number of degrees of freedom, and it grows with system size in such a way that you cannot reach times which are longer than this. Active matter examples are slightly different because we focus on a system which is forced continuously by the little motors, or there is injection of energy by some agents on the constituents of your active matter, and this is keeping your system out of equilibrium. And in many cases, we are interested in some steady state, which is out of equilibrium. You cannot describe it with the usual Boltzmann distributions and things like this, but is evolving in a slightly different manner from these ones over here. So we will try to also make this more explicit with examples and some calculations later on. Now, there is macroscopic here, and macroscopic is important because we are interested in the behavior, the collective behavior of a very large system with many degrees of freedom that interact in some way, and that they are able to organize or collectively decide something to be done out of equilibrium, but still in a very large n limit, where we can apply ideas and methods of statistical physics. So statistical physics in equilibrium relies on laws of large numbers, central limit theorems, these sort of things, which are properties of systems which are very large in size. Here, we are not going to use the same equilibrium assumptions, of course, but still, the fact of being in a thermodynamic limit, we call it also that way, a limit of a large number of degrees of freedom, will help us in many different senses, and will also be the interesting case we want to try to understand. So this thermodynamic limit here, this thermodynamic name, doesn't mean that we have the usual thermodynamics. It's just associated to this large n limit that will be important and the case we want to study. And then complex, okay, complex just means not simple, so complicated, otherwise we would have already solved it and understood everything about these cases. So complex is just here to say that they are complicated cases. So let me see what I wanted to say next. Good. Everything you heard until now, I think, because I came late, was about classical systems. But, okay, we have problems in physics, material science, classy, which are classical, typically classical because they occur at high temperatures, many degrees of freedom and so on. Active matter systems, so these occur at ambient temperature often, so okay, it's also classical kind of situation that one is interested in. Okay? But there are a lot of other experimental realizations which are also very interesting and that we could try to understand as well, which are quantum in nature. So people are very good at controlling atomic systems nowadays. And there is a lot of activity around quantum gases or different kind of quantum systems that either you drive externally and then you get close to this situation here. So I don't know, you have some electronic sample of some kind, and then you shine light, and then you have, kind of interaction, matter field interaction, and then electromagnetic, matter interaction, and then you want to understand what happens with the matter, but you drive it. So you are close to this situation here. Or else you can have other cases where you're not driving your system, but you want to see what happens, for example, with a bunch of atoms that people are able to put, I get the French word, so to trap, there's a word, so they are able to create like potential wells and get a lot of atoms here in some way, and then ask questions about what is the behavior of those atoms which are in interaction among them and that are confined to this space, and do they reach some kind of equilibrium configurations? Can I describe them after preparation in some way and then changing the trap or doing different kinds of manipulations? Is there some kind of equilibrium that characterizes this behavior, the behavior of these problems or not? And this can be essentially quantum. And in particular, in the context of quantum systems, people have started talking a lot about closed systems. So what do I mean by that? I mean systems that cannot interact with the surroundings, cannot exchange energy with the surroundings, cannot exchange particles with the surroundings, which are closed in the sense of microcanonical situations that you may be used to hear about in the statistical physics courses. And they have started asking questions about equilibration under closed conditions. And they started asking questions about how much the interactions between these particles, these atoms, influence the kind of putative equilibration that these systems will reach after some time. They don't have enormous amounts of numbers of atoms. Typically, they have thousands, let's say 1,000 or something like this. They are not in the limit of material science, okay? But still, you know, with a more or less large system size, what happens? Do these systems reach some kind of equilibrium or not? How this depends on the kind of interactions that they have. And this made classical people, like me, also, I'm half classical, let's say, a quarter classical, or 3/4 classical, and 1/4 quantum, let's put it this way. So go back to the issues of equilibration in classical physics as well. So, because many of the questions that these quantum people were asking were not really quantum. They were, you know, they had to do with the closed against open, because these other cases here are open. These are open. There is always a bath, and the system can exchange energy and sometimes particles with the bath. So these are open. But are the weird things that these people were claiming linked to the quantumness or linked to the closed character of the problem? So this made you know, a very nice, interesting interaction between quantum and classical that it's starting in a sense, and that some of us are sort of enjoying in the discussions and so on. So that you know, it's driving discussions, thinking, and so on and so forth. So let me draw a line here. My lectures will be classical here. I'm not going to talk about quantum, but sometimes I may comment upon the quantum extension of what I will say. Now, if I talk about open versus closed, classical, let's say, and I want to say something about the dynamics of my many-body systems. I have to start by giving microscopic dynamics to the constituents of those many-body systems. So in several talks, mine included on Wednesday, we very quickly wrote Langevin equations. But if you have a classical closed system, well, you don't write a Langevin equation, you write Newton, right? For the microscopic agents of your system. So what I'm going to do in part of my lecture today is I'm going to tell you how you go from this one to that one through something that, well, the quantum people call it reduction. Let me say it's integrating away parts of the system. And you will see how this comes about. It's not very, OK, thanks. I will use another one. There were, yeah, there's a big yellow one here. Thanks. So yeah, reduction or integrating away part of the system is what I said over there. So the nice thing about this calculation, which is very simple, as you will see, is that it gives you an idea of what is the origin of the terms that they are appearing in the Langevin equation. And in particular, what is the origin of dissipation? Where does it come from? And noise. And how these can be more general, are in general more general, than the ones that we write when we write the simple Langevin equations that you saw already in the talks these days. So why is this interesting? Well, it's interesting because you get a way of understanding where the Langevin equations come from, but also because some of us, when we study glassy dynamics in particular, we use something which is called dynamic mean field theory. And basically, what this dynamics mean field theory is to take your very complex system, focus on one variable, for example, one particle if you're working with particles, one spin if you're working with spins, and make some assumptions about what is the effect of all the other ones on the one that you have chosen. The one that you have chosen is not special, it's just any one. But the other ones, you know, they act like in a mean field manner on the one that you have chosen. This, of course, is an approximation. It's not exact in general, but for certain models, it's exact. And then what you do is you derive a generalized Langevin equation that takes into account not only the possible interaction of the system with the environment, but also the interaction of your selected particle with the rest of the particles. So then you get a generalized Langevin equation that is ugly. Okay, it's ugly, but you can deal with it. You can, do numerical analysis of that equation, and in certain cases, you can even solve it analytically. Okay? Of course, it's an approximation. There is this mean field here that corresponds to treating the rest of the system in some approximate way. But still, it gives you a sufficiently complicated Langevin process that captures some of the features which are observed for glassy dynamics in particular. And if you're interested in other kind of problems, like, for example, people who are doing ecology now and they work with Lotka-Volterra kind of equations, well, you can also derive that generalized Langevin equation for your selected species, let's say, in your Lotka-Volterra system of ecological system, and then try to say something about the behavior of that species that you have chosen. Okay. So it goes beyond the physical problems as well. It goes beyond the active matter. You can also do it in active matter and in different kind of situations. What will change is the macroscopic dynamics. So you may not start from Newton, but you can always start from some microscopic dynamics, integrate a part of it, and then get the effective Langevin equation that may describe the selected part of the problem. Okay? So what I'm saying here is that within this approach, the rest of the system acts like a bath on the selected variable that you have chosen, but it's not an external bath, it's an internal one. And it's self-determined in such a way that things work fine. Okay. So this is part of what I'm going to do now. But before getting into that calculation, let me go back to what we know from statistical physics, or what we know, do we expect when we think that our system has reached equilibrium. So what we expect is that ergodicity works. No, so if dynamics in equilibrium, what we expect is ergodicity, and the way in which I'm going to talk about ergodicity is about telling you about, time averages coinciding with the statistical averages. So time averages, what they are, say that you look at an observable, you take a limit of long times. I don't know how long they have to be, but okay, let's say something like this. Let me use the notation of particles. So what am I doing here? A is my observable. It is a function of positions and momenta of my particles. Say that I is the label of my particles. I'm putting arrows just to say that they live in d dimensions, say. And positions and momenta depend on time. I have the function of that phase space variable here, and I average it over time, over a time window that goes from t, the time at which I start my measurement, until a t plus tau, so something like this. Say that time is this is t, this is t plus tau, this is time. And, well, I suppose that I'm starting my measurement at a longer time than the equilibration time of my system. And this defines let me write it like this with an overline, a time average. And ergodicity states that this time average should be equal to a statistical average. And this statistical average should be, let's write it this way. Should be the average of my same function, now not time dependent, just a function of these phase space variables, weighted with some probability distribution, right? And this is the probability distribution in equilibrium that I expect for that system. So this is what I'm going to use as a synonym of ergodicity. And of course, in all those models that I'm discussing over there, the systems, this is broken, right? This is not necessarily holding. But this is what one expects in normal thermal equilibrium. Now, what are these? These, you know from statistical physics, depends on whether you're working with a closed system or with an open system. With a closed system, you will have the macrocanonical distribution. In an open, you will have canonical or macrocanonical if you also let the number of particles fluctuate, right? Now, let's just say that you are in a closed situation and that the only conserved quantity that you have is energy. Number of particles as well, but OK, I don't care so much about that. It's fixed. It's not fluctuating either in this other side of the open situation, so I forget about n. So if my system is closed, you know that the macrocanonical distribution tells you that you have to, the dynamics will move in a constant energy surface in your phase space, and that this distribution will be flat on that constant energy surface. So this P will be something like a delta function of the Hamiltonian of your system. Say that you have a Hamiltonian, normal, mechanical system. And this P will be a delta function of that Hamiltonian function set at the value of the energy that you choose with the initial conditions. OK? Now, imagine that you don't only have energy as a constant of motion. Imagine that you also have linear momentum, for example. In a mechanical system, it's a typical situation. Or angular momentum as well. So those are cases that you probably saw already in statistical physics courses. And, well, you have to add delta function of a few. Typically, there are a few. In normal, let's see if this one is, no. Normal cases, a few other deltas to be considered. Now, it turns out that in the kind of problems that these quantum people were using, often these problems were considered to be integrable. What does integrable mean? In my classical context over there, it's very simple. So what it means is that you not only have a few global quantities which are conserved, like energy, total momentum, and so on, but you have as many as degrees of freedom in your problem. So basically what you have to do in those cases, if a microcanonical description would work, is to consider all those constants of motion Let me call them I, mu. So these are functions of my phase space variables labeled by an index mu, which runs from 1 to n being the number of degrees of freedom in my problem. And what the natural extension of what I said is to say, well, I have to consider the product of all the constraints that I can build, so n of them, on these constants of motion, taking the values that are fixed by the initial conditions. So these I mu's with a curly I are the function I mu of xi, pi, evaluated at 0 time. This is my initial time. Of the dynamics, of the Newtonian dynamics of my problem. And so I choose my initial conditions. These functions I evaluate on those initial conditions. So they take some values. And then the microcanonical measure for these kind of problems natural extension is to say that I have to put them all the deltas there. Yes?
So when you have an extensive number of deltas, I would think the Jacobian would become important. But is something, the Jacobian associated with putting a nonlinear function in the delta? But I guess maybe Louisville's theorem is saving you or something? Because you have momentum here still? I don't know. This is a kind of a question.
No, you're worried about the normalization of this thing?
Yeah, exactly.
No, I think this doesn't pose a problem. Yeah, yeah, yeah. These things are macroscopic. So they scale with the number of degrees of freedom in the problem?
No, it's not quite the question, but it's okay. We can speak later, maybe.
Okay, we can discuss that. But you can define a density of states and do the same that you do with a normal case. Right? Okay, so these things are discussed. I mean, are discussed in the literature, and the motivation for coming to this problem again. As I say, comes from the quantum, so it's funny, no? It's people doing atomic physics experiments and that started discussing integrability in the quantum cases, which is a bit more difficult to define. But in this classical setting, this is quite clear. So this is the candidate for the microcanonical measure. Now, you know that when you go from the microcanonical to the canonical in the normal situations, the canonical measure, let me write it over here. The canonical measure is this one, right? So when you only have, in the microcanonical case, the energy as a conserved quantity, the canonical is the Boltzmann exponential factor, and this is what you have. Now, naturally, people have said, well, if my microcanonical candidate is this one, my canonical candidate erase this one and put it here. Will be something like this, where, here I had the Hamiltonian, now I have all the I mu's. And these would be extensions of the inverse temperature that would play the role of forcing that the average of these I mu's take the, if I want to have equivalence of ensembles, that the averages of these I mu's will be given by these tilde C I mu's here. Calligraphic I mu's over there. Of course, I guess that the worry that Jaron was mentioning is even more clear here, because if these objects are order n, and I have a sum over order n things over there, it looks like I have an order n squared in the exponential, and that this would be a little bit bizarre thing. Not extensive, but super extensive in the number of degrees of freedoms in the exponential. But this doesn't seem to be a problem, because when you do actual applications, at least the ones that people have done until now, this gamma mu scale in such a way that everything arranges so that this becomes order n. So if you were worried about that, don't worry, or I mean, worry, and at least there's not so much, for the moment at least, there's no big problems in this sense. Now, we heard this morning a lot about maximal entropy things. Sometimes people justify this exponential form using a maximal entropy argument. Now, I'm not going to discuss this because it's not the context of my lectures, but I just want to ask you to think about this problem during the weekend and, you know, maybe discuss or become a little bit suspicious about these maximal entropy things. So maximal entropy, what is it? You want to estimate a distribution function, so you want to estimate a px of x, let's say, starting from some, well, let me call it S, some entropy expression, S of x, that you say, well, is dx px of x log px of x, no? Okay, and then you ask that you say that you know that this piece of px of x is normalized, and that you know, for example, that the average of x under this piece of x is equal to something. And you use this constraint and the normalization constraint, and you say that this is an extreme, and then you obtain the exponential distribution for the x. Okay. Now, think about defining y equals to x squared and defining sy just like this, but with the y, py of y, and think about what happens. But you will get a different result. So do the calculation, think about it, and see that there is something a little bit fishy there. Who was asking? That, for example, if you want to relate the S of y, so you write the S of y, you write it in terms of P of x, you will have an extra term. It will not be just this, they will have an extra term with Px as well. And then if you want to say, okay, I extremize this with respect to P of x, I get something else. I don't get the exponential.
Under the same constraint?
Yes. So this is just, you know, an aside.
Sorry, maybe I'm...
I don't want to discuss this.
Okay, okay.
Who was asking? Jaron. No. I know, you. Okay. It's an exercise for you. You know, it's not the subject of my lecture. It's just a beware sort of thing. Okay. So why am I telling you about this? Because there is a lot of activity about trying to understand when, you know, the dynamics of a problem which is closed, you evolve it with Newton evolution, a classical one, and you ask whether it reaches a distribution function when you look at a piece of it, like what we do, you know, in normal statistical physics. So you focus on a piece of it, and you ask whether it reaches a distribution like this or not, and under which conditions. Just to have a look at these, which are called generalized Gibbs ensembles, and discuss whether they're relevant or they're not relevant. So now I will go back to what I announced as this reduction calculation, but next week, what I'm going to do is I'm going to work with a very simple model that I can tune it to be in this class or in this class, and I can use it to show why here it is not able to equilibrate to the Boltzmann distribution because of features that you will see. And it is a model that, it's a mean field model for coarsening problems, like Anton's was discussing, and I was discussing a little bit as well in my colloquium. And when you write it in this way, you can ask the questions about, does it go to a Boltzmann, generalized Gibbs ensemble, and for which parameters? So you can do both. You can do the analysis of the dissipative relaxation and the analysis of the non-dissipative evolution, and study these issues about equilibration towards normal Boltzmann usual distribution or the generalized Gibbs ensemble ones. And it's sufficiently simple to be solvable in different ways. So it's illustrative. OK, all this I said. Other questions here? Questions? OK, this is very introductory, right? OK, so let me prove then Langevin equation, or derive it. So imagine that you start from a huge system which is composed of your system of interest. This is the one you're interested in, and the rest that I'm going to call a bath. To make my notation simple and not very long, I'm going to consider that my system is just one particle, and that is a particle that lives in one dimension, so that I don't have to write arrows and indices. So the system is one particle in D equals 1, and then I characterize it with position and momentum. Okay? And now the rest, the bath, I'm going to choose a model for the bath. And I'm going to choose the simplest model, which is going to be an ensemble of harmonic oscillators. Let's write it like this. Say that they all have the same mass. Sorry, let's call it pi, so that I don't use the same notation for something else. Okay, so these are the momenta of my oscillators. These are the positions of my oscillators. And these are the masses of the oscillators. Let's say they're all equal or not, doesn't matter. Okay, let's put it different. And the internal frequencies of the oscillators. And I have NO oscillators. For the particle, I have some Hamiltonian of my particle. And then I have to say that, how do I couple my oscillators to my particle? So I will have an interaction term that I choose to be of this form. So these are coupling constants. These are the positions of the oscillators, and this is a function of my position of the particle. I choose it. It's a model. I choose it to be this way. So for the model of the bath, you can say, I could have taken something much more complicated, but if I take something complicated, I cannot solve it. So this is like a, first order Hamiltonian. I mean, some perturbative Hamiltonian that may come from some much more complicated one, and I just keep the relevant part at the lowest possible order. OK, so now what I have to do, if my system is closed, the big one, the whole system is closed. So I have Newton's equations for everyone. So I can write Newton's equations for my system But of course, the oscillator will appear through this coupling. I can write the Newton's equations for the oscillators, but the coupling to the system will appear also through this. So there will be forced oscillators through this term here, and there will be also influenced particle because of the coupling to the oscillators. But all this can be written down. It could be, I can write it, but it would be a little bit long to write it. I'm not going to write it. I'm just sketch the steps of what has to be done. So what you have to do is write Newtons, solve Newtons for oscillators under f of x. It's a linear equation. You see, it's a linear set of equations for the oscillators because they are oscillators. So if you solve for the oscillators, what you will get is expressions for pi of t, qa of t, and they will depend on their initial values and f. Then what you have to do is insert in Newton equations for x and p. And what you will get is an equation that looks like this. And up to here, everything I'm saying is exact. Here. So what I get is an equation that looks a little bit like the Newton equation, but it has some extra terms. And I will explain those extra terms in a second. I'm forgetting here this one. So this capital F here is the deterministic force that was already there in the Newton equation for x, because here I had consider something like this. For example, just normal kinetic energy for my particle plus a potential. So in that case, the F here would be V prime of x of t. With prime is derivative with respect to the argument, right? Minus, okay? So this term here is the normal inertia term of Newton. This term here is normal force of Newton for the particle. But then there are two extra terms that appear. So there is this one, and there is this one. Imagine that f, the function that I chose to couple to my oscillators, is just x, to make things simpler and to maybe let you see the kind of Langevin equation that you are used to see. So if f is x, this is 1 in that particular case. All these factors, this is 1, and this is 1. And you start seeing something that looks like a normal friction and something that looks like a noise. I haven't told you yet what's the functional form of this gamma, nor what is this psi. Okay, but I will tell you in a second. But you see that this looks like a friction. And this looks like a noise. Now, in the case in which f is not just linear in x, what I have, well, it's something, here I see it more clearly. I have multiplicative noise. If I understand this like a noise, I have the noise that multiplies a function of x. So the kind of Langemann equation, I will convince you in a second, that I'm getting, in general, for general, if f has multiplicative noise. So if it's not the yellow case I'm discussing, let's see if this one is visible. If it's this one, it could be multiplicative noise. Because it multiplies the noise with a function of the variable itself. This is what is called multiplicative noise in general. If f is linear in x, this one is 1, and then it's additive noise. So below is additive. Now, if I come here I have a function of time which is integrated. Everything is integrated here. So I have a delayed friction over there. So everything is delayed friction. And now let me tell you what are these gamma and what is this psi from the exact calculation, so that you can see what do they depend on and what we can say about them. So okay, now I have to check my notes because these ones I don't remember I had. Otherwise, I will put wrong factors. Here you are. This is 1, and the gamma. Okay, so these are exact expressions that you get just by integrating the equations for the oscillators and replacing. So what can you say here? First thing you can say is that gamma is symmetric with respect to t going to minus t prime, t going to t prime, and vice versa. You can see that it depends on Ca squared, the coupling constants, and that you have a sum over all the oscillators. So it's natural to think that the nice scaling that you need, so that when you take the number of oscillators to infinity, something that you want to do, because if you want to mimic a bath, you imagine that the bath is a big thing. So the bath should be made of a lot of degrees of freedom compared to the system. The system has only one. So this one, okay, you expect it to be, to be a bath. You have to take an O to infinity. But if I take an O to infinity, I have a divergent thing over there. So the natural thing to do is to say that I will rescale Ca by 1 over square root of an O, so that here there will be a 1 over an O. And here there will also be the good scaling that will appear within an O's. This is detail. I could have done it at the very beginning, scaling over there, and I could have obtained it immediately here. But it's a detail. But this is a function, right? This is a function. Now, this one is more interesting because this one depends on properties of the oscillators at the initial time. Something that you certainly don't know. It's a huge system, and you're not going to go and look at each of them one by one to say what are these. So what is done here is to say, well, I'm going to assume that I know this in probability. So this is the assumption that takes a deterministic problem, because at the beginning everything was deterministic. So this is the big jump towards a stochastic problem that one makes, saying that I know the probability of the PIs of 0 and the QAs of 0. One proposes that. And one proposes that saying, well, I have a bath. A bath has to be, I expect, something in equilibrium, say. So let's assume that the bath is in equilibrium at temperature T, or inverse temperature beta. And let's assume that that equilibrium is such that it's oscillators. So I know then that the average of this is 0. I know that the average squared of this scales like the kinetic energy. So it's kBT. And I will ask that the average of all these things is 0, and that the squared average is also proportional to kBT. So basically what one does is to say, I assume that this is the canonical equilibrium measure of the oscillators coupled to the particle at the initial time. So this is a Gaussian distribution, you see, because they are oscillators. So you can compute the average, you can compute the correlations of this function psi. So if you do those assumptions, the average of psi is going to be 0 at all times. And the correlations of psi at different times will be kBT times gamma of T minus T prime with the same gamma which appears in the friction term. It's just a calculation that you have to do. Okay. So you see that when you, this square root will be OK here, because when you correlate this with this at a different time, there will be CA squared that will appear, and the normalization will be right. So OK, it's just a question of doing the calculation. I have hidden you one little thing that I'm not going to discuss. Let me put it here between parentheses, because it will take me a little bit of time to discuss it. There is one little thing missing to get this exact equation that I wrote here that is corrected by something which is called a counter term. Let's not get into that discussion, but if you're interested, we can discuss it in private, but otherwise it will take 15 minutes, and it's a bit long. So the important thing is this. You see that you make this assumption on the ensemble of oscillators that takes you to a stochastic equation via this introduction of a probability distribution. So it's here that you're putting the non-deterministic nature of the dynamics and the stochasticity of the problem. The friction was there. The friction was not needed, I mean, to say anything. It was just a function that you get, and that's it. But the noise is coming from this assumption over here. And now we have this very general Langevin equation that we have obtained by reducing the full system. So I want to use this word again. It's the reduction of these whole systems towards the one that you focus on, which is just the particle, that we have used or have put in practice to get this equation over here. Other questions here? Yes.
Is it important that you have these harmonic oscillators? Could you have an ideal gas instead, and would this work?
Yes, but you have to, it's a different calculation, right? But
simpler one, perhaps?
You mean with no potential?
Yes, with no potential.
I know that people have done the collisions, okay, you know, through the collisions, you can also get a Langevin equation.
Okay, you need some mechanism to exchange between the bath and the
I think so.
system.
Yes, I think so.
An ideal gas wouldn't do the job.
I'm not sure, yeah.
Okay.
Yeah. Yeah, it's a horrible calculation, but there is a very nice paper by Hangi and Dunkel from MIT, I mean, when he was a student, where he did the thing of the collisions for the relativistic case to get something like a relativistic Langevin equation, and that's can be done. In the same idea, you know, you single out one and you look at the collisions of the other ones. So this calculation I showed you is due in different contexts by Swansig and Kawasaki in the classical setting that I'm telling you about. And it was due, similar idea, exactly the same one, by Vernon and Feynman for the quantum problem, where you work in the path integral representation, but the idea is the same. You integrate away an ensemble of oscillators to get an effective path integral for the system that you want to focus on. But it's the same, using oscillators to be able to do the calculation exactly. Now, of course,
Letícia,
yes, please.
So then, if you take the probability distribution, let's say that, let us suppose that I know them by the experiment.
Yes.
Then you can rebuild your own Langevin equations.
Yes.
And everything will be contained in the noise, actually. Correlations in the noise.
Exactly. So if you change this assumption, if you say, well, my bath was not in equilibrium, actually, because it was an active bath, let's say. And imagine that you know something about the non-equilibrium steady state of your bath, which is not Boltzmann, but it's something else. Well, you know, you repeat your calculation, you do the averages, and you see what you get. And most probably, I mean, surely, what you will get is something that does not balance the correlations of the noise with the friction. Because you see, the fact that the gamma that is here is the same as the gamma which is here is a consequence of having used here the Boltzmann distribution for the oscillators. If I hadn't used Boltzmann, the canonical one, for the initial positions and momenta of the oscillators, I would have gotten here something else, I don't know, some function of times that could even be non-stationary, I don't know, some other thing. So I wouldn't get a balance between what is here and what is there. And that will be a signature or a consequence of the fact that my bath was not in equilibrium.
Right, yeah. And moreover, the way that you are coupling the system and the bath also plays a role, no, in the sense
Not so much so, you see, because it appears only in the multiplicative noise and in the friction, but it's a balanced way of appearing. I mean, it's I could put any crazy function of x here, and I will get this equation with the f primes and so on, but it will be this equation. So it doesn't really, it's not the bath, it's the system that it's deciding that. But of course, I mean, with multiplicative noise, you can get all weird features of the dynamics of your particle afterwards. So in that sense, it will be important, yes. Some other questions? Okay, so this is what Carolina was asking is very important because you have a balance between the friction and the noise term only if you assume that your bath is in equilibrium. If you don't assume that your bath is in equilibrium, you can get any other kind of thing. So for example, you can get, imagine something like, I don't know, whatever. You know, a different function here from there. So let's say gamma 1 here and gamma 2 there. And this will correspond, it will tell you, an equation like that is telling you that your bath is out of equilibrium and necessarily is going to drive your system out of equilibrium as well. Now, the explicit form of these gammas depends on the characteristics of the bath. Depends on what is here, you see? So even in the case of an equilibrium bath, you can get different functional forms for the gamma, depending on how you choose the characteristics of the oscillators. So maybe you have seen in the literature, of course you have seen white bath. So what is white bath? It's just gamma proportional to the delta function. But you can have other kinds of functional forms. That's my chalk here. So gamma t minus t prime twice gamma naught delta of t minus t prime. This is white noise, the one that you're used to. But then you can have things like gamma naught e minus t prime over some characteristic time, or power law decays. With some prefactor here. Different kinds of baths, depending on how you choose your oscillators. This, of course, is the more common one in the context of Brownian motion that we are used to, but could be other things. So in particular, there is quite a lot of activity related to the inverse problem in the context of Langevin processes. What do I mean by that? Well, we heard about the inverse problem this morning, but imagine that now you have a problem of a tracer moving in some medium that you don't know what it is. So typically, a tracer moving within a cell or within some biological environment. And you want to characterize the environment. So you follow the motion of your tracer. You get trajectories, some trajectories. And what you want to know is which is the Langevin equation that generated those trajectories. So you want to guess which is the capital gamma 2, if there is a capital gamma 1, if there is a little f. This is what you want to know. And there is a lot of activity around this problem. It is a difficult problem. It's a statistical problem, which is very hard, because typically people don't have very long trajectories in time and don't have so many trajectories either. It's a difficult problem. So there is a lot of activity around this. So let me remember what I wanted to say next. Good. Now, let me, as I said, so let me tell you about dynamic mean field theory in a second, and then tell you about some examples of different kinds of dynamics and how one characterizes out of equilibrium relaxations and dynamics and so on in the context of Langevin processes. So what is dynamic mean field theory? In a really nutshell, is to write an equation like this. Let's imagine that this little f, I can forget about it. This little f, I can forget about it. I can forget about it over there. I will have the effect of the external bath, because if I have a glass, it's coupled to an environment. So there will be the external noise. So there will be m x dot t. Say that the external noise is white to make things easy. So this will be the part of the external noise. There will be the external force, if there is one, that the particle is feeling. There will be the noise from the external bath. And this is the friction of the external bath. But then there will be the effect of the rest of the particles on this one. And what dynamic mean field theory does is that it represents it as friction and noise. So there will be a term here, let me call it eta of t, and there will be a term here that will have a face like this. Let me write it like this. So I will write it like this. So this eta here is going to be a noise that is not going to be white. It's going to be given by some correlator, let me call it D. And the friction here, notice that I wrote it, instead of writing the derivative of the particle position, so instead of writing the velocity here, I wrote it as it was integrated by parts. Turns out that it's better to do it this way. So this is like integrating by parts here, and saying that the f doesn't count. It's not, it's the f is equal to x. So I have 1, but I integrate by parts here. I drop the border terms, and then the derivative comes here, right? But this correlation of the noise eta and this integrated friction of that I have from the internal degrees of freedom are not in equilibrium. They don't come from a bath in equilibrium. They come from the system itself. So there is no reason why the D, which is here, is related to the sigma in a simple way. But what dynamic mean field theory does is that it allows you to write this D as a function of I will define the correlation and the linear response of your system, and this sigma let me write it again. Also as a function of the correlation and linear response of the system. Let me define this C and R. So C is the correlation of X with itself at different times. And little r is the linear response. So it's the variation of X with respect to a perturbation that is applied at the other time t prime and then set to 0. So this is a linear response. This is self-correlation. And these angular brackets here, what do they represent? They represent averages under these dynamics. So averages under the dynamics with both noises, psi and eta. So it's a self-consistent thing, you see? What you should do if you want to play this game is to solve these equations, get the C and the R, plug it in the D and the sigma, and for certain models, you know the functional form of the D and the sigma. So functional form of sigma and D known. Known under assumptions, as I told you. I mean, it's not that you can derive it exactly. But you can do reasonable assumptions that allow you to get the functional form of this D here in terms of C and R, and this sigma in terms of C and R. And then you have a closed set of equations, right? You have a Langevin equation that give you the trajectories, but the trajectories under a noise that is self-determined by the trajectories themselves. So it's a thing that goes like that, yeah. It's a linear response. R is the linear response. So what you have to do is, let's put a little h here. So you have to compute the trajectories under the little field, variate with respect to the little field. So I will do an example maybe on Monday of how to compute these kind of things. And this is what is, the linear response. So simple cases are those where, for example, D is just a power of C and there is no R here. And sigma is a power of C times R. So for those of you who know, perhaps, our beloved p-spin model. So a very much studied model that I will discuss next week allows you to make this procedure explicitly, analytically until the end, because for these models, when the number of degrees of freedom of the system goes to infinity, you not only work with one particle, but many, of course, and in the limit of many particles, then you can derive D is just a constant over 2c to the p minus 1, and sigma turns out to be, with a p here, sorry, j squared over 2 p minus 1, c to the p minus 2 times r. So there are cases where this procedure can be done analytically until the end, and this recursion can be derived, and this d can be derived, and this sigma can be derived, but there are special models. So this is a very special model, which is what we call a mean field model. In general, for particles in interaction, this cannot be done in finite dimensions, but there is a way to do it in infinite dimensions. So interacting particles living in dimensionality going to infinity, this procedure can also be done until the end. So this is work by Zamponi, Jorge Kurchan, and other people, this part here. Okay. So of course, this doesn't solve the problem. This just poses the starting point. And but OK, it's a way to see that these Langevin equations that you certainly have seen in different contexts also appear in the context of these complex systems as an effective approximate description of them that take into account not only the coupling to the bath, but also the internal coupling of the variables within your system. Questions? Yes.
Yeah. So why is this called mean field?
Oh, because these problems are called mean field, these models.
No,
okay.
This I agree. Just before that, I'm thinking about where are you making an assumption about?
Here?
Yeah.
Well, you see, in a generic problem, you cannot close your evolution equations into functions of 2 times only, or 2 variables only. Or you see, the correlation depends on the correlation between 2 positions, 2-point correlations, and the linear response as well, if you write it in a slightly different way. In general, you will have to take care of 3-point correlations, 4-point.
I see.
You will not be able to close the hierarchy of equations, the BBGKY equations.
Okay, just you are making a cut. Yeah, okay, I see.
It's a closure that one does, which is exact for certain cases, like this one and like that one, but it will not be in general.
Right. And the fact that you know D and sigma.
Yes.
And so you need to have a good dedicated guess for that, or I mean.
No. This again for these problems you derive it. For those problems you derive it, and in particular for this one is particularly simple. But in other cases, it's not that you can guess it.
Okay. You really need to reach it.
By you reach it.
Okay.
You reach it by derivation, by analysis of the equations.
Okay.
Yeah. Now you see that in this particular case, you can see via the eye that there is a very simple relation between D and sigma, because it's like sigma is like the derivative of D with respect to C times the response. So we will come back to these kind of relations are fluctuation dissipation-like relations that, well, tell you about, already you can see that if these relations were not as simple as it is, you can guess, you can conclude that the microscopic dynamics of your problem was itself weird. It was not Newton, it was something else. But okay, this is a little bit early to say it. Let me see what I wanted to tell you. Okay, so now that we have a setting for the starting point, okay, notice that these equations, of course, I can go back to the Newtonian case if I switch off the friction and I switch off the noise. So this equation contains everything I want to discuss. It contains both the dissipative and noisy Langevin dynamics, relevant for glasses, but it also contains the case of closed Newtonian dynamics that I would like to discuss in the last lecture. So it's a good starting point. Now let me, in the last 10 minutes, just say a couple of things about separation of timescales that typically appear in all the problems that we and you look at. So imagine that you start from the Langevin equation for a very simple problem. One particle in a white bath, white noise, equilibrium bath, and just additive noise, so very simple. So you have just this equation to care about, and with the noise which has the white noise correlations. Now, this is a very nice problem because if you choose this force F in different ways, so for example, you can choose it to be minus k times x. So like this, I'm thinking about a harmonic oscillator. This is the potential that my particle is feeling, and this is k. So this problem is linear in x, so it can be solved. You can solve this equation, and you can compute everything. So you can compute what happens with the average of the particle under the noise, and you will see that, say that you start from some x naught here, and you let it go. You let it go, the average will go to 0. You can compute the average of velocity, or the momentum, say, of the particle, and you will see that it also goes to 0. In particular, you can have a look at how this one goes to 0. And you will see that it goes to 0 with a characteristic time, let's call it Tp, exponentially with a characteristic time. And this Tp, let me write it here or here, is m over gamma naught. This is a very simple calculation you can make. So there is a characteristic time after which the average of the position of the momentum, sorry, let's focus on the momentum, goes to 0, and you can compute any other property of the momentum. For example, the momentum squared, say over twice m, and you will get that in the same time scale, it goes to kBt over 2, which is equipartition in the same time scale, and you can compute any other kind of property of the momentum, and you will see that actually it reaches the Maxwell distribution. It reaches e to the minus p squared over twice m, normalized, as it should, after this time scale. So it turns out that in normal applications, this time scale is very short. So very quickly, for t larger than this value here, all properties of the momentum of the particle become equilibrium-like. It equilibrates, very quickly. Then you can say, well, actually, but it's like I have two variables. I have two space variables in these problems. I have P and X. I just told you what happens with P. What happens with X? So if you have the potential, X, as I said already at the beginning, it will also go to 0, its average, its squared average will go to equilibrium distribution. There will be another equilibration time for X, another characteristic time that you can compute. How did I call it? Tx, let's call it. Tx, which is typically much larger than, or larger, depends on the parameters, but it can be larger than Tp, for X to equilibrate. This one depends on K, of course. K, the width of the harmonic potential. And depends on K in such a way that if you take K to 0, it diverges. And what does this mean? It means that, if you started with a confined particle in a harmonic potential, it will equilibrate to Boltzmann in the harmonic potential because you have a harmonic potential. So not only this will happen, but also E minus, well, there was a beta here, sorry, I forgot. The beta V of X will go into the asymptotic distribution of my positions. But if K goes to 0, there's no longer V. V goes to 0. And if K goes to 0, this is 1, and this is no longer normalizable. If K goes to 0, non-normalizable in an infinite size system, in infinite volume. If I put walls, well, it's like putting a harmonic potential. So if I don't put walls, this equilibration time for the position diverges. But the one for the momentum is still finite. It's the same. It's the m over gamma naught. So think about what I've done. When I did the integration over the baths, okay, I integrated away part of my system, the total one, which I consider to be the bath, and I got rid of it. Now I'm focusing on my system, which I say is also a harmonic oscillator. If it's a harmonic oscillator coupled to this huge bath with a force that derives from a potential that confines the particle, it goes to equilibrium, both momentum and position. But if I just set this harmonic potential of the particle to 0, I have one phase space variable that equilibrates, which is the momentum, but I have another one which doesn't. So I can have coexistence of variables that live together in the same system, but one equilibrates, the other one doesn't. And you can trace that back to the fact that the Hamiltonian is P squared over twice m plus V of X. This one is always there. So it's like a harmonic potential for the momentum that is always there. But this one, if I kill it, I don't have any more potential for the position, and the position doesn't equilibrate anymore. So this is important because in complex systems, you can have certain variables that equilibrate and others that don't. And in particular, people who were doing numerical simulations like 20 years ago, they were sometimes checking equilibration of their samples because they wanted to do equilibrium analysis, looking at the kinetic energy. And this is a bad observable because the kinetic energy does equilibrate because of this. But the positions of their particles, the structural organization of the particles in the liquid that they were looking at, perhaps they were not in equilibrium. They didn't check that. Okay? So it's very important to realize when you have a complex system with different kinds of variables, some can be in equilibrium with the bath and some can not. You have to be able to know what you want to look at and what you want to focus on. Okay, I think it's maybe time to finish for me. Oh, no, I still have 4 minutes. So, okay, let's see if I have another thing, quick thing to tell you now. No, yeah, the other thing, quick thing to tell you now was that if I look at what happens when the potential is 0, You saw from Jasna, for example, today, she was showing some mean square displacements. So those mean square displacements for this particle, for example, if you calculate it and draw it, what you will see this is the mean square displacement. So you look at how the particle deviates its position between 2 times, t prime and t, the displacement it made. You square it, and you average over the noise. So for these problems, you will see that this mean square displacement has 2 time scales. So there will be a time scale where this goes like t squared, and there will be another time scale where this will go like t. And the crossover occurs at m over gamma naught. The same time scale is just a calculation that you can make. So this is ballistic behavior. This is diffusive behavior. So now I'm looking at one variable. And one variable can have 2 regimes in its evolution. 2 regimes which are distinguished by, in this case, the time delay at which I look at it. So this is time, this is t prime, this is t. The equilibration time went to infinity. So I'm really far away from any equilibration time for x. But during all this evolution that it takes place, depending on how far away or how nearby I look at my variables, I see different time dependencies. I see t squared or I see t. So this is to say that I can have, not coexistence, but different time regimes. In the behavior of a single variable. And if you look at, for example, instead of just the normal Brownian motion I was telling you about, but if you look at active Brownian particles, like the ones I told you about in the colloquium, you will have 4 regimes. So you will have a ballistic, a diffusive, before the particle realized there was the active force, then another ballistic controlled by the active force, and then finally another diffusive at the end. And the diffusive coefficients will be different here and there. So here is when the particle didn't realize there was the active force, and this is the part which is dominated by the active force. So, dynamics can be very, very complicated, even in a very simple case of just diffusion. And this is the difference between this and this is here I have an extra ingredient, which is this active force that introduces these 2 other regimes on top of these 2, which were these 2 over here. And of course, the crossover here is still the m over gamma naught, but these ones will depend on the active force, on the value of the active force. OK, now I think it's a good moment to stop.
Any questions?
So just to be clear, this last scenario is still for k going to 0, this last scenario that you presented here?
Yes. Otherwise, if you have k, this will saturate to a value that depends on k. But when k goes to 0, it doesn't.
Okay.
I have one question here.
Yes.
In the case that the question Professor Carolina asked, when you have non-equilibrium, you have a different gamma function.
Yes.
You can still call this a Langevin equation?
Yes. You can call it a Langevin equation because Langevin proposed the Langevin equation for the Brownian motion problem, right? With a very nice article that I recommend you to read because it's very simple and nicely written. But then we were using Langevin equations, in many different contexts. And a kind of justification of why these equations make sense in other contexts is the derivation that I did at the beginning. There you understand what you're doing. You're considering your system coupled to an environment, and then depending on the different properties of the environment, you will have different noises and different frictions. But they're all reductions of a problem where you throw away pieces which you don't know very well, and then you make some stochastic, probabilistic assumption about those variables, and you focus on the ones that you really want to understand.
Oh, thank you. Maybe it's a very primitive question, but what do we mean by equilibrium when there is no K? Well, K is 0.
There is no equilibrium.
There's no equilibrium, right?
Right.
So when you say the particle doesn't equilibrate, what do you mean?
Here, in this context of this example?
If equilibrium is everywhere, or
say it again?
Why would we say that there is no equilibrium instead of saying that equilibrium is along, everywhere?
Well, equilibrium you want to associate in a problem which is open to a Boltzmann distribution, right? You want to say that, let me say it this way. You want to say that the ergodicity hypothesis I told you about, so you want to say that the time average of this quantity here should be equal to the average of this quantity with some measure. But this is not normalizable. This will give you infinity. This will give you infinity as well, but OK. It's not, yeah. There's a lot of things which are going on during the evolution here that you don't, they don't go to a constant, to a finite constant, these objects. Right? So,
thank you.
It's funny that because actually we write down the Hamiltonian for a free particle and you don't think about that.
Exactly.
Sometimes.
This is a very simple example that I think it tells you a lot of things. There are other properties, I should have replied you better actually. There are other properties of equilibrium that, for example, that I can discuss next week, is that if your dynamics reached say that you look at the distribution function of the position and the momentum at a given time t. If you reach Boltzmann canonical equilibrium, this should go to E minus beta kinetic energy. This is kinetic energy, let's call it this way, minus beta potential energy. Now this one is 0. So when you want to normalize that, you will not be able to normalize it, but you will get an infinity there. OK, now let me take a problem where this exists, the V exists. If you have a problem where this really exists and equilibrates your evolution, when you look at correlation functions like this, for example, you can prove that this should be a function of t minus t prime under these conditions. And that having reached this distribution, one can show that actually the correlation function between any observables should become stationary. This is what's called stationary. Well, in the diffusion problem, this is not true, because if you calculate this thing, you will get the minimum between these two times. The result of this calculation is mean between t and t prime. It's not a function of t minus t prime. So you break stationarity. So you break another property of equilibrium dynamics that this problem is breaking. Right? So it's another way of saying that.
First, thank you for the nice talk.
Thank you.
I wanted to ask you, there you explained very briefly about the ADPs and these return to a ballistic regime after the diffusive regime, like you have diffusive, ballistic,
exactly,
right?
Because this one is driven by the active force. So once you have gone beyond this time regime where just the normal diffusion without the active force occurs, then you have like a particle under a force.
Right.
A particle under a force will do ballistic motion. And this is why you have this t-squared. Of course, it could be that for small values of effect, this time scale is mixed with this one, and for not sufficiently high temperature, this other time scale mixes with that one, and then instead of having these very nice, broken lines that I showed, you get, of course, something more like this. Huh? So this depends on the values of this parameter, kBt, and m over gamma naught. Okay. That will for certain choices, make these distinctions very sharp.
Okay, and a follow-up question is,
Yes.
If I quit the inertia of the particles, let's say, if I put them in an overdamped regime, do I have like one breakage in the line?
It's like saying that you just completely ignore this first part.
Okay.
And then you will start from here.
Okay, thank you.
Yeah, that's the overdamped regime.
Thanks.
So the overdamped regime is just saying that you focus on times which are, and time differences and everything, which are longer than this time scale.
Right.
And in normal situations, this time scale is very short, so it's okay to do it. Yeah.
Okay, thank you very much.
Yes.
Yes. When we have this correlation, the noise correlation in different times, we have this correlation depend of this gamma function, right?
Yes.
And this gamma function depend of the bats, right? Yes. And if I have another, no, I don't know, it's isotropic bats, I don't know, this noise correlation it's different, I think.
Exactly. The function gamma will depend on your bath. So, if you have other kinds of variables, people have worked with spin baths, for example, or, other kinds of baths, then you will get other functional forms for the gamma. Okay. That depends on the bath.
How can, I don't know, how can I construct this gamma function? There are some...
I mean, you don't really construct it. You say, which is the best gamma function that will represent what my bath is. This inverse problem I was telling you about, where you have the tracer moving in some environment that you don't know. What people do is to try to extract these gamma functions. And typically, they are gamma functions which are not deltas. They have some time delay and, sometimes exponential decays, or it depends on the problem. So, yeah.
Okay, thank you.
Another question? I have a little question.
Yes.
If you see, when you look at this, this correlation, the white noise correlation, if I think about Brownian active particles,
yes,
I go to have that, but not that.
No, it depends, because Brownian active particles, what we normally do is we put translational noise, which is like this one. Yeah. It's just equilibrium bath, and that's the one that controls the translational noise. And then there is the noise that controls the orientation, and that's the one that breaks the equilibrium assumption.
Okay.
There is the one on the, because if you remember the F act that I wrote the other day, it was F act times an angle, basically, the cosine of theta of t, something like this. And so there was a vector, it's a vector, so there's a cosine and the sine. And this theta is doing a random motion. Right. So if you solve for theta, here you will have the other noise. But this term will be a horrible, complicated noise term, but it doesn't have an associated friction to it. So this is the one that breaks the equilibrium assumption of the bath, because the orientation is moving differently from the translations.
I see. Okay.
Yeah.
Okay.
Yeah.
Nice. So if there is no other questions,
that's another one over there. Yeah.
It's nice to keep the shape,
Yeah. Yes.
Hi. Thank you for this interesting lecture. I have a question regarding the Langevin equation. What happens if time in the integration goes to infinity, meaning neglecting time frame?
I'm sorry, what happens if what goes to infinity?
Time goes to infinity in the integration.
There's no problem. You mean, let's see if I understand what you mean. You mean in this integration here, in the one of the friction?
Yes.
Well, you cannot take it to infinity here and not take it to infinity in the other terms, right? Because this is the time that it's in all the other terms as well. So the equation is causal, it's causal. Here you have mx dot of t plus this thing, and the other terms are also evaluated at the same time, external time t that is here. So, and this integral goes from the initial time to the measuring time, and this is completely causal, okay? So there is no problem. I mean, you can follow, for example, you can integrate step by step this equation and construct the solution for a any trajectory, for each trajectory. So there is no problem in going to infinity following your trajectory.
Okay, can we say that is related to the memory effect?
I didn't understand. What is it?
When we extend the time to infinity, is that means that we remove the memory effect on the system? Memory effect. Memory effect.
The memory, no, you keep it. No, you keep it. You mean that this thing is going to 0 when times get very far away? And then, in this sense, this decays with the time difference. You're right with that. So what is very far away is weighting less in this integral. You're absolutely right. But this time t prime goes until t. So, there is part of the memory that will have an effect on what you measure in time t as well. Yeah.
Okay, thank you.
That's, yeah.
Okay. Oh, yes. So that's the last question, and you are allowed because I'm going down.
Thank you, Letícia, for your talk. My question is, we can change or choose a specific gamma which we can modify the ballistic regime or diffusive regime to a subdiffusive regime, for instance?
Sure. Yes, of course. So if you, for example, get gammas that decay as power laws, with some power there, this power will show up here. So you can get subdiffusion or superdiffusion depending on the kind of power that you have here. So yeah, so this is called the Hurst exponent. The one that comes here and that it's then, actually it's Hurst exponent when it's seen at this level of the mean square displacement, but it comes from that thing over there. And actually, there are people, for example, experimentalists who look at biological things and they extract, as I said, the gamma. They extract it from looking at these kind of quantities. So they look at correlation functions between the positions of the tracer at different times or the displacement of the tracer at different times. They measure this. They get some exponent here, and then they say, well, the gamma that gave me that was something. A half, typically they find.
Although it's tricky because it can be a finite time.
Of course, it's tricky.
Yeah.
Sure, it's tricky. Yeah.
In the perfect case, yeah.
Typically, they get subdiffusion and a half.
I won't ask if there are any other questions. So if you want to ask Letícia,
I'm here, so we can
thanks
discuss.
a lot.
Thank you very much.
See you on Monday, and see all of you on Monday. So enjoy the weekend, but be safe to come back on Monday. Don't kill yourself in São Paulo, and don't drink too much, and don't do whatever you want. Okay. I don't care what you do, but come back on Monday.
Just very quickly, when you leave the auditorium, please take your stuff with you so that we can lock the auditorium, okay? Thank you. Water bottles that